So you can see these two terms, map and reduce, in this diagram. Map and reduce are terms that actually come from functional programming languages. I don't know if you've done any course on programming languages, or if you've done programming courses on languages like SML or Scheme or Lisp, or one of the functional programming languages. But those languages have uh, these mapper and reducer functions, and the job of the map function is to take another function f and take a list of items. Okay, I'll just call it a1 to an, and then return a list where this function f is applied to each of the elements. So apply the function f to the first element, apply the function f to the second element, apply the function f to the third element, and so on. In other words, apply the function element by element to this list and then return the resulting list. That's what the map function does. It takes an existing function f. So this, note that in functional programming languages you can have a function taking in another function as an argument. So it's a different kind of programming paradigm as opposed to imperative or object-oriented languages, where in imperative languages there is a sequential flow. Um, so whereas here you tend to think of functions more as mathematical functions rather than as doing a sequence of operations on a on a piece of data that is input to the function. So you don't have to know about this. I'm just trying to explain why these terms come, where these terms come from. So think of the mapping task here, or this function f here, as corresponding to splitting the documents and generating these tokens. Okay, so that's what this function f is doing, and it's being done on this entire split. So these individual items here are like the splits. Okay, and all the splits don't fit into a single machine. So what the mapper does is, or what these mapper machines do is, they apply the same task of parsing. Okay, so this f is the parsing function. They apply the same task of parsing on each individual split, right? And this can be done here because these tasks can be parallelized. The kind of computation that you're doing here allows you to parallelize these parsing tasks by splitting your corpus into these splits, right? Maybe you can think of other kinds of tasks where it may not be possible to parallelize uh, the overall task into these by splitting them into individual splits and then parsing each split independent of other splits, right? So not every computation problem can be distributed in this particular way. Okay, so that's one thing you have to keep in mind, that is, you can't just take an arbitrary computation task and split it into a map phase and a reduce phase. So what the mapper does is, it takes each individual split and parses it and outputs the result into these partitions, and then the reducer sort of aggregates the results generated by different mappers into some kind of an aggregated output. So think of the reducer as combining, aggregating, or reducing these different results into a single value or a single output. So this index construction algorithm we saw was one instance of Mapreduce. I also explained very briefly to you how the task of computing the word count can be implemented using the same Mapreduce framework, where the mapper is just going to take a split and generate a stream of term comma 1 ordered pairs, and the reducer is going to take all the ordered pairs where the term part is the same and then just add up the counts for those individual terms and present that aggregated output into some output file. Now, one of the things you have to note here is that this particular mapping of each individual partition to an inverter is done in a very specific way. So let me write this down here. The inverter will receive the term comma doc ID pairs in increasing order of lexicographic order of terms. Okay, by increasing order I mean lexicographic order, since we are talking about terms here. So that means all terms that start with an A will be input to the inverter first. Then later on you'll get terms that start with a B. Right? So the terms are already sorted in the very way in which they are presented to the inverter. Right? They are not sorted here, but this distributed framework is going to present the ordered pairs of a particular partition in sorted order of terms. So if the inverter wanted to generate the postings list for a particular term, it just has to look at what sequence of documents are associated with that term. Okay, and that sequence will be coming into it as a contiguous chunk of ordered pairs. Right, and once it receives that chunk, it just has to sort that chunk by doc IDs and then generate the postings list. Then it will take the next term in lexicographic order and again look at all the doc IDs that are coming in with that term, and they will all be bunched up together. So it just has to take that entire sequence and then sort it in increasing order of doc IDs and then write it to the output. Similarly, in the word count algorithm, using this Mapreduce framework, the words will be presented to the inverter in increasing sorted order. Right? So the inverter just has to take all the ordered pairs for the same word and just count how many ordered pairs there are for that particular individual word and then write down the count for that word. Is that clear? This is something you as a programmer don't have to do. This is something that the framework itself is doing for you. Right? So what you as a programmer have to do is to just write down the code for the parser and the code for the inverter. You will be using this distributed framework that has already been created and standardized on a cluster of machines. Right? It's just like using a particular programming language. Somebody's already built that language, and you're just using the that particular language to do the task that you want. Similarly, when doing this distributed computation using Mapreduce, you will use an existing distributed computing framework that somebody's already built for Mapreduce and then write down your individual programs by specifying what the parsers and inverters are for your particular task. Right? So the parser for the word count algorithm will look different from the parser for an indexing algorithm. The inverter for a word count algorithm will look different from an inverter for the indexing algorithm. Now there is an open source implementation of this kind of distributed Mapreduce framework. It's called Hadoop. So if you install, so Hadoop is an open source implementation of Mapreduce. Open source implementation of a Mapreduce framework. If you install Hadoop on a cluster of machines, so Hadoop is written in Java. So if you want to use the Hadoop framework, you will need to write your parser and inverter in Java, and this implementation will take care of all the underlying details. It will take care of what the master is doing. You don't have to deal with the master at all. It will assign the individual nodes of the cluster, the jobs or the roles of parsers and inverters by itself, and it will assign these partitions to the inverter by itself in again in sorted order of terms. You just have to write the code for the parser, taking in whatever input you are, and then transforming that input into this output, and likewise taking in this particular input that the inverter is receiving and transforming that input into this output. So this index construction algorithm we saw is one type of Mapreduce algorithm, and Mapreduce is a more general framework for distributed computing, uh, where you don't have to write the code for the distribution part. You just have to write the code for the parser and indexer. And the original Mapreduce paper was written by Jeff Dean and Sanjay Ghemawat at Google, because they first used Mapreduce for the Google indexing system. And that paper describes how they used and how they built this framework for doing the task of distributed indexing. So that paper is available online if you want to read it. Now, your overall problem could perhaps be split into not just one single map and then a reduce phase, but you can have a sequence of map reduce phases, right? So the output of this diagram, for example, could be the input of another map reduce algorithm, right? You can chain together a sequence of map reduce tasks. And actually Google's indexing system is a sequence of Mapreduce tasks. It's not just a single Mapreduce task that we just saw. What we just saw was just one of the phases of their algorithm. Now, one of the things that you may notice from this diagram is that the final inverted index that is built is partitioned by term. That is, each part of the index is defined based on what terms appear in the dictionary in that part. So this is called a term partitioned index, where one of the machines is storing a sub-range of terms. So the postings list for that particular range of terms are stored on this particular machine. So it's a term partitioned index. You can also think of a document partitioned index, where one machine is handling a sub-range of documents, right? So that means for each individual split, we are building a complete inverted index. Okay, so the parser is parsing the document, but then the inverter is building the full index for that particular uh, set of documents. So it's called a document partition index. So what will be stored over here will be the index for documents 1 to 5000, say. What will be stored on this machine will be the index for documents number 5001 to 15,000 and so on. So that's called a document partitioned index. Of course, the index itself will have terms, right? So there'll be it'll have terms in the dictionary and then postings list corresponding to the doc IDs. Now, why would you choose a term partition index or a document partition index? How do you decide which one to choose? Well, think of uh, a scenario where certain celebrities become very popular, right? Let's say before the elections, some politicians may become very popular. Lots of people may be searching for the same name, right? For example, before the US elections, queries like Barack Obama, Sarah Palin, and so on were very popular at that particular, uh, uh, in that particular duration of time. So imagine a term partition index where you know uh, uh, Sarah Palin uh, appears in this particular term partition index, and likewise, Obama may appear over here. Whereas in other partitions, you may not have terms that are being searched for very heavily. So in that case, most of the queries would be directed into this section of the index, and that could increase the load on this particular machine, right? So the load can be distributed very unevenly if you have a term partition index, because certain terms may be a lot more popular than other terms, and there is no way to, if you just partition based on terms, there's no way for you to prevent one machine from being bogged down by queries, right? Just because some particular entity or place or person may become suddenly very popular. So what most search engines use is a document partition index, which allows you to do load balancing. Because if you have a document partition index, then a query for Barack Obama, for example, will be served not just by a single machine, but by all the machines, because all each of these machines will be storing a particular range of documents, and Barack Obama is as likely to appear in one particular range than in any other range. So the load can be distributed evenly across these machines, even for popular queries. So we'll talk more about this if we come to the chapter on web search, which is basically chapter 20 in the book. So here is a more general presentation of what we just discussed for indexing. This is a more general presentation of Mapreduce. So the map function in Mapreduce is going to take the input, like recall that the input over here was a split, and it's going to transform the input into a list of key value pairs. Okay, so k comma v is a key value pair. It's an ordered pair. Now the key for the indexing task were the terms, and the values were the doc IDs. But in general, any MapReduce task is going to have a mapper which will transform the input into a list of key value pairs, and then the reducer will be assigned the keys of one particular partition, and the keys will be presented to the reducer in sorted order. So for every key that the reducer gets, the reducer will somehow combine the values for that key associated with that key, and then either aggregate them or list them, or modify them, massage them in some way, and write them down in the output. So in the reducer for the distributed indexing algorithm, for example, the keys were the terms, right? So terms from A to J were assigned to a single inverter or reducer. And the terms are presented in sorted order. So for a particular term, all the doc IDs associated with that term would have been sorted by the reducer, and then that particular sorted list of doc IDs essentially becomes the postings list for that term, and then that postings list is written into the output. So that's what uh, these two lines show. The mapper is taking the split, converting it into a list of term comma doc ID pairs. The reducer is taking the all the key value pairs where the key is the same, and then the keys are being presented to the reducer in sorted order, and then it's just grouping together the list of doc IDs and then outputting them into postings lists. Is this clear? There's actually an example here, very simple example. Uh, let's say that the mapper is assigned this split. So there are just two documents in the split. The first document says Caesar came, Caesar conquered. The second document says Caesar died. So when the mapper parses these two documents, it's going to tokenize them and normalize the terms. So this term becomes um, C comma D1, came comma D1, C comma D1, conquered comma D1. The second document, when it's parsed, will generate the key value pairs Caesar comma D2, died comma D2, and this will be output into the partition. The reducer will first be given all the key value pairs where the key is equal to C. Note that the first key in lexicographic order over here is C. So C will be the first key that's given to the reducer, and all the values associated with that key, right? A value like D1, for example, sorry, not D1, yeah, D1 here, D1 here, D2 here, will be assigned to the reducer. Now these need not be sorted, right? So because the reducer will be picking up these values from different machines, they can come in any order. In this case, this D2 comes before D1, even though here, this sequence is D1, D1, D2, but you can think of, some other machine dealing with D2, the second document, and that could come in any order. They need not be sorted. So this reducer will then sort it. Okay, so it will generate, it will sort it into D1 and then D2, and note that it's noting down how many times this word appeared in this document. So this is the term frequency of Caesar in document D1. This is the term frequency of Caesar in document D2. Similarly, it will take died comma D2, which is just a single key value pair for the same key, and then it's just going to become died comma D2 colon 1, which is the term frequency of the term died in the document D2. Right, so this is just the inverted index. Right, this is the postings list for Caesar, this is the postings list for died, this is the postings list for came, and this is the postings list for conquered. Any questions about index construction using Mapreduce?